Hi, everyone. Today we're going to be reading pages 46 and 47 in your physics workbook, and we will be specifically looking at Newton's second law of motion. So, as you can see on the top of page 46, it says, what is Newton's second law of motion? Well, which is harder to push, a full shopping cart or an empty one? Who can cause a greater acceleration on a shopping cart, a small child or a grown adult? Now, you can probably answer both of those reasonably easily, but why is it harder to push a full shopping cart versus an empty one? Or why can a grown adult cause greater acceleration than a small child? What's the science behind it? That's what we're really going to be looking at here. So let's start by looking at changes in force and mass. So suppose you increase the force on a cart without changing its mass. Okay, so the mass stays the same and you're pushing harder. The acceleration of the cart will also increase. Your cart will also accelerate faster if something falls out. Okay, this reduces the mass of the cart and you keep pushing just as hard. So the acceleration of the sled that's pictured on the bottom here in figure 2 will change depending on the mass of the people on it and the force the sled dogs apply. Newton realized these relationships and found a way to represent them mathematically. So as we get into the next paragraph, determining acceleration, here's the key concept with Newton's second law. Newton's second law of motion states that an object's acceleration depends on its mass and on the net force acting on it. And as we can do with a lot of things in science, we can represent that type of relationship mathematically. So it says this relationship can be written as follows. The acceleration of an object equals the net force applied to it divided by its mass. So what that means, looking at the formula, the greater the net force that's applied to an object, the greater the acceleration, okay? But the greater the mass of the object, since that's on the bottom of the equation here, the less the acceleration of the object. So this formula can be rearranged to show how much force must be applied to an object to get it to accelerate at a certain rate. And so if we simply switch around those variables a little bit, you'll see that it says the net force equals mass times acceleration. Okay? So let's look at figure 2. Got kind of a cool picture here of some sled dogs, a sled team, and some folks riding on the sled. It says, suppose that 4 dogs pull a sled carrying 2 people. It says, use words and fill in the pictures to show how you can change the dog-person arrangement to change the sled's acceleration. So how could you increase the sled's acceleration? Well, a few things you could do there is, what if you had more dogs being added to the sled team? So instead of having 4 dogs pulling the sled team, what if you had 6 or 8 dogs? That's going to give you more force. Or you can start removing passengers, okay? Because that's going to decrease the mass of the sled, which if you have less mass, that should result in a greater acceleration. Now the opposite here, how could you decrease the sled's acceleration? Well, to decrease the acceleration, we would have to start removing some of the dogs from the sled team. So dogs could be removed, thereby having less force, or we could have more passengers added to the sled. So have all 4 passengers on the sled versus just having 3 or 2 or 1 passenger. That's going to have greater mass, and the greater mass you have, the less acceleration. Let's move on to page 47. It says acceleration is measured in meters per second, or as we've talked about before, meters per second squared. Mass is measured in kilograms, kg. Newton's second law shows that force is measured in kilograms times meters per second, or kilogram meter per second squared. This unit is also called the Newton, which is capital N, which is the SI unit for force. 1 Newton is the force required to give a 1 kilogram mass an acceleration of 1 meter per second squared. So that just kind of shows you the science behind why the Newton is used as the unit for force, okay? Now let's take a look where it says do the math and kind of this funky looking car that's going off the edge of this platform. It says every year in cities around the world, teams create cars, push them across platforms, and hope they will fly. Unfortunately, the cars always end up accelerating down into the water. So the first question says, if a 100 N or 100 Newton net force acts on a 50 kilogram car, what will the acceleration of the car be? So we need to remember that if we're looking for acceleration, from what we saw on page 46, acceleration equals force divided by mass. So we're going to look at this and realize that, okay, the force applied to the car is 100 newtons, and the mass of the car is 50 kilograms. So we would have to take 100 newtons divided by 50 kilograms. 100 divided by 50 is 2. And since we're looking for acceleration, the unit is going to be meters per second squared. So the correct answer there, 2 meters per second squared. Now let's look at number 2. It says after that same car leaves the platform, gravity causes it to accelerate downward at a rate of 9.8 meters per second squared. What is the gravitational force on the car? If we're looking for force, we're going to take the mass of the car times acceleration. Okay, so from number 1, we can see the mass of the car is 50 kilograms. We're going to take 50 kilograms times the rate of acceleration, 9.8 meters per second squared. So 50 times 9.8 is 490. And since we're looking for force, the unit is going to be newtons. So the correct answer there for number 2, 490 newtons. Okay, let's quickly take a look at the assess your understanding questions on the bottom here, beginning with number 1, letter A. It says, what equation allows you to calculate the force acting on an object? So if we're looking for force, Newton's second law says force is going to equal mass times acceleration. So the correct answer there would be force equals mass times acceleration. Okay? Let's apply that to letter B. It says, what is the net force on a 2 kilogram skateboard accelerating at a rate of 2 meters per second squared? If we're looking for force, we have to take mass times acceleration. So the mass of the skateboard is 2 kilograms, and its rate of acceleration is 2 meters per second squared. So 2 kilograms times 2 meters per second squared, that's going to give us a net force of 4 newtons. So the correct answer there, 4 newtons. Finally, letter C, they're asking us to predict. If the mass of the skateboard doubled, but the net force on it remained constant, what would happen to the acceleration of the skateboard? So we're doubling the mass, but keeping the net force the same. Well, Newton's second law tells us that if the mass of an object increases and the net force stays the same, its rate of acceleration is going to be less. So the correct answer here, the acceleration of the skateboard would be cut in half, okay, and would end up becoming 1 meter per second squared. Okay, if you have double the mass and you keep the same net force, you're going to have less acceleration. So let's wrap this up with the got it section on the bottom. It says, now I know that Newton's second law of motion describes the relationship, and the correct answer here would be among force, mass, and acceleration. Okay, so now I know that Newton's second law of motion describes the relationship among force, mass, and acceleration. So that's pages 46 and 47 dealing with Newton's second law. Again, if you have any questions, please don't hesitate to reach out and let us know.